If we have this a 3D representation of this molecule and we want to change it into a Newman projection, we want to draw the Newman projection around carbon 2 and carbon 3. So always be specific around what carbons you're drawing the Newman projection around, because you have 4 carbons in this case. So we're going to start by, we're going to view the molecule from the side here, from this angle. So along this line. So the first thing that I'm going to see is carbon number 2, and then the second one at the back is going to be carbon number 3. Okay. Now for carbon number 2, what I have, just to draw it exactly as you see it. So what I have here is the CH3 in plane. So this is the CH3 in plane, and it's pointing in plane. Okay. And then I do have a bromine and the hydrogen. Now, any group on this side of the Newman projection is going to be in front, and any group on the other side of the Newman projection is going to be at the back. This makes it easy in order to fill out the groups. So I need the bromine to be at the back, so I'm just going to put the bromine over here to be at the back. And then my hydrogen is going to be in front. I'm done from carbon number 2. So let's go to carbon number 3 in here. Carbon number 3 has the CH3 in plane. Do you see that? The CH3 in here. So always put those on vertical. This is the long carbon chain. Put it on the vertical line. And then you have your CH3 at the back. So I'm going to have my CH3 at the back in here. So if I ask you what is the dihedral angle between the bromine and the CH3, the dihedral angle is going to be, in this case, 60 degrees. And then I have my hydrogen over here, fill your CH3s, and this is going to be the Newman projection. So you can see that the dihedral angle between both CH3s in there is 180 degrees. And the dihedral angle between the CH3 and the bromine is 60 degrees. So definitely there will be some sort of repulsion between them. It's similar to gauche repulsion in there, even though it's not 2 carbons, but it's a bromine and a CH3, so we can still call it a gauche. So gauche is whenever big groups, they approach each other and their angle, their dihedral angle is 60 degrees. So let's draw the Newman projection of substituted cyclohexane. Here I have a tri-substituted cyclohexane. I have 2 CH3s and an ethyl group. This is a CH2 and a CH3. The CH3 here is pointing at the back. This one is in front, and the ethyl is in front as well. So the first step I would do is I would change this into its most stable chair conformation. If you haven't watched the video on how to change the cyclohexane into its most stable chair conformation, please do that before proceeding with this explanation. So over here, I'm going to end up having my 6 carbons in there. Okay, let's go ahead and label the axials and the equatorials. So I'm going to end up having this carbon being up, so its axial is going to be up. The axial of this one is going to be down. The axial is going to be down. This axial is going to be up. And this one is going to be up. And this one is going to be down. Drawing the axials and equatorials are a must before drawing the Newman projection. It makes it really easy in there. Let's go ahead and number. So I'm going to give those numbers 1, 2. You can number anywhere you want, because I'm not numbering for the sake of naming. I'm numbering for the sake of putting the substituents. So if I go ahead and do this as carbon number 1, this is going to be 2, 3, 4, 5, and this one is going to be 6. Now I've labeled all my axials. Now let's go ahead and label the equatorial groups. And for the equatorial groups, if the axial is up, then the equatorial is going to be down. So you position your equatorial down over here. Axial is down, equatorial is up. Axial on 6 is down. Equatorial is going to be on the opposite direction, so it's going to be up. This is going to be down, and this is going to be up, and that is going to be down. So now I've labeled all my axials and equatorials. Now I'm going to go ahead and put my substituents in there. So my CH3 here is down. It needs to stay down. It cannot stay up. So on carbon number 1, it needs to be down, and down is the equatorial position. So here I do have my CH3. On carbon number 3, I have my ethyl group being up, so it needs to be on the axial position. And on carbon number 4, the CH3 is up, so it has to be on the axial, on the equatorial position over here. So see, it's very important to label your axials and equatorials first. It makes it easier. Keep the same orientation. So this is going to be up and this is going to be down. Sorry, it's up. This one is going to be up, and then transfer the whole thing. So now I'm going to go ahead and change this into a Newman projection. I know that Newman projections are around 2 carbons. Here I do have 6 carbons in the cycle. So I can, if I look from this angle over here along this line, I can draw a Newman projection between those 2 carbons in here. So let's put a circle in there. You can easily view that. And then another Newman projection between carbons 1 and 2. And then put a connection between those 2 Newmans, having carbon 6 and 3 being the connection in there. So if I'm looking down this angle over here, the first thing I'm going to see is carbon number 4. Let's draw our 2 circles. That is carbon number 4 over here. And that is our second circle, which is supposed to be carbon number 2. Okay, so you have carbon number 4 and carbon number 2. Let's finish up from this Newman projection and then draw the other one. So carbon number 4 has a hydrogen pointing down. Of course, all the other axials and equatorial bonds, these you fill them with hydrogens. There are no other substituents other than hydrogens here. So on 4, I do have my hydrogen pointing down. Okay. And then this is going to be connected to carbon 3. So 4 is going to be connected to carbon number 3, which is this carbon over here. I'm just going to go ahead and write carbon number 3 for now. And it's going to be connected to a CH3 on the other end. Okay, so this is how I'm going to say it. 4 is connected to carbon 3. It's connected to the CH3, and it has a hydrogen pointing all the way on the vertical line. Now 4 is connected to 5, so the circle is going to be carbon number 5. And with 5, this is what I have. With 5, I have the hydrogen on the side. I have a hydrogen being on the vertical line, and then on this other side, it's connected to carbon 6. So I have a hydrogen here, I have a hydrogen here, and then the vertical line is connected to carbon number 6. Moving along, let's go with carbon number 6 here. So actually, let's go with carbon number 3 because the 2 is in front. It's easier for me to fill the front than the back. So with the 3, it's connected to carbon 2. So immediately carbon number 3 is going to be hooked to carbon number 2. And then on this side, I have the hydrogen. So this is going to be the hydrogen. And here I have another hydrogen. And then at the back, I have carbon number 1. Carbon number 1 has the hydrogen being vertical. So the hydrogen is going to be vertical on carbon number 1. And then the CH3 is on the side. And then carbon number 1 is connected to carbon number 6. So carbon 1 is connected to carbon number 6. And this is going to be the Newman projection in there for this structure. Now, yet I did not put all the substituents because on carbon number 6 it's a CH2. So we can take carbon number 6, erase it, and put a CH2 in here. Make sure that you put all your substituents. On carbon number 3, it's a CH and an ethyl group. So I'm just going to go ahead and take this one out and put a CH and then an ethyl group in here. As simple as that. Make it simple because it is not difficult. And this is going to be the Newman projection of cyclohexane. Every Newman is around 2 carbons. So 2 carbons here, 2 carbons here. This is 4 carbons. And in the middle, there are 2 carbons. So you have a total of 6 carbons. These are the carbons of the cycle.